something that he's doing is pushing this biomarker out to where nobody's ever been before, and that's really cool.
So hello and welcome to the Sheekey Science Show, where in this video I spoke with Aaron King. Aaron's been involved in various longevity projects for the last 10 to 15 years. He has written overviews of the network of longevity organisations, as well as giving an overview of scientific pathways to better understand the aging process. Most recently, he has built this tool AgeRank, which enables us to visualise how different biomarkers are changing with age. We discuss this and more in this conversation.
So there's some basic information that's missing for the field of aging research, and one of those things is that we don't have a list of all the things that change with age. If you just want to know like what actually changes with age and what doesn't change with age, it just doesn't exist. So in pursuit of that, I built this system. I call it AgeRank, but it's just a biomarker visualization system. And up here is a search bar at the top, and you can take a look at any of these biomarkers. This is all NHANES data for now, from the Center for Disease Control. They did this National Health and Nutrition Examination Survey. I think that's what it's called. NHANES is the shorthand for it. And so they have all these biomarkers that they measured about 100,000 people over the course of like 20 years, a bunch of different cohorts. Anyway, you can take a look at any biomarker and you can see whether, what it looks like over the lifetime, for cross-sectional data. So let's just take a few here, like this, and we go to go. So we can see like, alkaline phosphatase, it changes rapidly during development, and then it kind of flatlines for the rest of life. So it doesn't really change after you're done with development. Aspartate aminotransferase never changes over the course of the life, really. Alpha-1 acid glycoprotein seems like it's increasing as people get older. There's a cutoff with the data here. So this system, the reason why it looks the way that it looks is because I've seen everyone else's data when it gets presented during these conferences or online, and it's just really bad. The box and whisker plots, the line graphs, they don't capture what's actually happening. And a lot of times when people present data, they present it that way because they know that they don't have enough data to really like accurately show the conclusions that they're coming up with. So they're trying to hide the fact that they don't have strong data, and that's why they use these weird displays. So I really like scatterplot. And this red and the black dots here are the floating point mean and median.
Okay.
And you can tell a lot of stuff. I'm going to stop here for just a second and ask if you have any questions about what's going on here, or something that I might have skipped over.
Yeah, for sure. So, firstly, how long does this take you to make? And also, are there any intrinsic limitations with the current data set that you're using?
It took a while. It took like, I don't know, like a couple months. The underlying philosophy took like years to develop, just like of watching like all these different what's going on in the field. But the actual data, I would say that the code, I got some help with that from an outside source. I actually hired somebody to rebuild the whole thing in JavaScript. But the code is actually really relatively simple. The data, manually formatting NHANES data took a really long time, and I did that myself. And I would say that that's the biggest part of this, is getting the data into a format that can be displayed easily in a scatter plot, that can be understood easily by this system. Because you can't script it. So if you go to the NHANES website and you go look through all their data files, from year to year, they change the naming systems. They change the organization. Sometimes a biomarker will be in one category and then it gets moved to another one. And then sometimes it's named one thing and it changes names. And sometimes they switch their methods. So there's a lot of kind of like, I guess, unique biology knowledge and statistical knowledge that you need to have in order to deal with the underlying data set. But once you can format it, which I did, then it becomes really easy to just visualize. You were asking about limitations. So all of this is cross-sectional data, and there are specific situations where it might be the case that cross-sectional data shows one thing and longitudinal data shows another thing.
Right.
So as soon as I can get longitudinal data into this system to compare against the cross-sectional data, then we can see like what the differences might be. And it shouldn't be that difficult, but currently, like I applied to get access to the Baltimore longitudinal study. We'll see how that goes. But there's I think there's a lot of longitudinal data that can be put into this relatively easily. It just takes time, I guess, to get access to a lot of stuff. NHANES is free, or it's public, so it's the easiest data set to access.
Interesting, because I mean, obviously this has taken. It looks like this has taken ages to generate and put it together. But obviously this is an incredibly useful resource that you've built, and so I guess the question is, what do you see as the use case for this, and what interesting findings have you already observed?
So in terms of gender-specific differences, alanine transaminase is pretty interesting. The sex hormones and all that kind of stuff, it's very obvious that those show gender differences. But if we look at alanine, you can see if we go to male, and the demographic tools are over on the left-hand side here. And so you can just go to male, and you can see this really huge arc. And then when you go to female, all of a sudden that arc just kind of disappears. It's much less of a change over time. And we can look at different years of NHANES data, and we can see the same trend. This is important, that being able to swap out plot sources, I think, is really important. Being able to swap out medical ranges is really important. You can change, like, look at different medical institutions, like optimal range for all these things. Anyway, so again, here's the female for 2017 data, and here's male, right? And so we can see, if you're like, when we try to change these things, when we try to figure out like what things are part of aging for who, sorry, let me back up. If we know that for females it doesn't change, and for males it does change, then we actually know, like right now we have an example of a mechanism for how, like, what is going on in women that allows this to be the same over the course of their entire life. We can actually look at this and study it, and then just observe and say, hey, we know how to do it. Now, it might not be tenable, like it might be tied into basic biological functions. And so it might be like, oh, well, we just can't change that right now. But we do know it's possible. It's possible for a human being to keep their alanine transaminase pretty much the same over the course of their entire life. Let's see if there's any other interesting for the other male, female aging only. This was interesting. Total bone mineral content. Let's go back to this and go to DEXA scans. Total bone mineral content. Okay, so here's female, and then male data. What did that look like? That's okay. Yeah, so you can see that for the male data, it stays more constant, and then for the female data, it has this drop after age 50, which, if anybody can guess what happens at age 50, 40 to 50 for females, it's very obvious. Menopause related, potentially. So this is the kind of stuff, and we can take a look at all these pieces. We can get a list of everything that really changes with age, and then that allows us to understand, okay, here's what aging is. And then what you can do is you can take all these interventions that people are doing on for trying to get anti-aging to work, and you test it against the whole list rather than just like a few biomarkers. Right now, most people, I would say that pretty much every longevity clinic, what they do for you is they tell you to not be fat, don't smoke, and get an MRI. And that's essentially what longevity clinics do. They don't have a list of all the things that change with age, so they can't actually like measure the totality of aging for anyone. Um, anyway, that's what this system was supposed to. One of the things that this system was supposed to solve. Now the site's slow, and that's because that's on the site's end because I'm hosting it on not the most expensive host, but hopefully I can transfer it to a more faster backend host, and then it'll be better. Okay, so this is high sensitivity C-reactive protein, and I see it mentioned a lot by various aging organizations or labs or clinics. And we can see that it has this it starts to go up with age. But if we take away everyone with greater than 25 BMI and we take a look at the data, magically it's gone, right? Like the
Yeah.
aging has disappeared, right? So these black dots are median. And maybe I should have explained this before, but the average for all these, it doesn't matter what the average is because what you can get is pathological subgroups, subpopulations that will pull the average up, even though for most people a biomarker is staying relatively flat. And so the median is really what we're interested in because everybody ages. And perhaps I should have said this sooner too, but there's two tenets that are kind of guiding this whole thing, which is one is that everybody ages, and two, anything that changes with age is part of aging. So that guides us towards finding out what this median curve looks like for all these different biomarkers. Because if the median, like whatever the median is doing, that's what we're really concerned about as far as aging is concerned. The averages, again, so like you can see it where when the red gets pulled away from the black, it's a sign that there's a pathological subgroup that's artificially pulling up that biomarker curve. And if we can eliminate that and get that red to be on top of the black, then it becomes a really strong, much, I guess, more true state of things. The last one I'm going to share here is cystatin C, which is a very resilient biomarker. It doesn't seem to respond to BMI. It doesn't seem to respond to like wealth level or gender. Everything that you do to this, just the curve looks exactly the same, where it just rises with age and then eventually it goes out of bounds and your kidneys fail. So this type of biomarker is like a really strong, like this is like a core part of aging. Other biomarkers, they can actually be solved by just not being fat. I think I'm starting to repeat myself here, so I'm going to stop here and ask if you have any other questions or comments at this point.
Of course. I mean, so firstly, just as you mentioned, the cytostatin C was this already known as a well-established biomarker? And obviously this has been proven by your plots. Okay. And so obviously this is really good data set, and I love it because it gives the attention to specific individual markers. Because I think what got me focused on this AgeRank that you've created was you made a post on LinkedIn saying that biological age is unnecessary, and I think that's kind of possibly a bit controversial given like how the field is at the moment. And so therefore I'm wondering, what are your views on this concept of biological age given what you've just showed me?
So the theory it makes a lot of sense, right? Like the biological age concept is like, oh, chronologically I'm one age, but my body is in a different state, and people they accumulate damage at different rates and they have different rates of regeneration. And so you might find one person at age 40 that seems biologically very similar to this other person who's at age 30. And so the concept at a high level makes a lot of sense. But when you put it into practice, you get a bunch of biomarkers. You combine, this is not for the methylation biological ages, this is for the biomarker aggregation biological ages. They get a bunch of biomarkers, they put them together, they come up with this weighted average, and they say, you're this age. And then you go, great. So how do I fix my age to bring it lower? And they go, oh, well, okay, we'll split it back into its core components, find the thing that's the worst, and then target that thing with an intervention. Well, then why are we combining it together in the first place? Why don't we skip that whole first step and just go straight to the individual biomarkers and just, you can tell me which one's bad, and then we'll go, like, it's a completely unnecessary step at the clinic level, because you can't interact with biological age to any degree. There's no therapy that simply targets biological age. It has to target a specific something that's specific, measurable thing. And I've been in the back room for some of these clinics, and the way that many of them come up with biological age is they kind of just have people sitting in a room and they go, you feeling what I'm feeling? Yeah, that sounds about right. And they have like these weights that they just kind of arbitrarily come up with. And that's why they're all different from each other. That's why some of them are just very far off from what your real biological age is because it's just kind of based on feel, and just sort of arbitrary weighting systems. So that part of it, the concept is a good concept. It's just, it doesn't have any practical use at this point, the way that people are doing it right now. And if you think about it, what they're really doing is they're trying to get a bunch of biomarkers, combine them together, and give you a percent health rating. Like if you're in a video game and you're 78% healthy, right? That's essentially what this number is. No doctor on the planet has ever done this for anybody in the history of medicine. It would have been really nice to have in medicine to go in the doctor and the doctor tells you you're 80% healthy. That'd be cool to know, kind of. But nobody does it that way because it's a really useless tool. Like, you go, oh, I'm 80% healthy. What do I do about that? Oh, well, and then they'd have to find the thing that's making you not healthy and target that. So it just doesn't make a lot of sense, in general.
Yeah, that's
From
a
my
good way of
opinion.
describing it. I know as well that you've taken a look at, so like Bryan Johnson's been very open with all of the data that he's collected. What did you find from looking at that data set?
It was interesting because I'm back and forth. So I don't like what he's doing. I look at what he's doing and sometimes I'm just rolling my eyes like, oh, this guy. But I went through all of his data and I found out that most of his biomarkers are either like dead center at the median of human population, or they're at like sort of like the edge of 1%. And so for every single one of his biomarkers except for one, he's gone to a place where people have already been. And those people didn't spend $2 million to get there. They just, per year, they didn't spend that money to get there. He hasn't really broken out except for red cell distribution width, where if we look at his data, it falls like far outside of the scatterplot distribution that NHANES has, at least. I don't know if for any other biomarker databases, but at least for NHANES, he is far outside the distribution, and he's lower, on the lower end. Red cell width rises with age, so the lower that you are, logically, it just makes sense that it's better. And I was thinking about this, and at first I was thinking, well, he's only got one biomarker. But then I thought, he's got one biomarker. Like, that's actually a really huge achievement. Being able to break out of, like, that's the distribution and go to a place where it looks like nobody's ever been before, that's pretty big. So I think I'd like to validate that. Like, I don't know if like how well it's measured and stuff like that. There's all sorts of like things that could have been wrong with it leading up to him putting it up on his website. But if it's true, then it is a big deal. It's actually a pretty big deal because that means that you can actually take these biomarkers that we see these distributions for, and if he can get outside of the bounds of what everyone else is doing, then something in his whole uh, I guess routine, some of seems superfluous, but something in there is clearly working. Something that he's doing is pushing this biomarker out to where nobody's ever been before, and that's really cool.
Exactly. And I think, well, this kind of leads on to my next question, which is what is the sort of idealistic solution to how we could go about looking at people's age and how we can treat it? Because obviously measuring so many biomarkers there's a lot of work to take all those measurements from an individual. Or so I guess what's the solution? Are you trying to find what are the most effective biomarkers that we should look at and sort of reduce that list to a smaller subset, or are then we eliminating information that's actually quite insightful?
Yeah. People want to have this short list, this like best list, and I think that it's possible to get there. For me, the first step is let's get a list of everything that changes with age, and some of them will be tied together. So one biomarker, like other biomarkers might be stacked on top of like one core biomarker. And then if you just measure that one, you'll get this other 30, you'll know the state of these other 30. And that's really good. If it works out that way, then fantastic. If it doesn't, it'd be nice to know how expensive it really is to measure everything that changes with age. And to get to that point, which is kind of like the next phase of this whole operation, which is to figure out once I get a full list of everything that changes with age, then we can figure out, okay, how expensive is it to measure these things? How accurate are all these tests? Some of them have a lot of natural variance, and so like how close are we to even measuring them correctly and all that kind of stuff. Um, I think that the pursuit of a short list right now is premature, but then again, I'm not in with the NIA or the NIH right now, so maybe they have better information about this than I do. But I just think that it's premature at this point to try to get a short list.
Yeah. No, I mean, at least based on what you just showed me, it kind of makes sense that we're still very far from fully understanding what's happening, and so it's too soon to jump to conclusions. And so this kind of leads me on to the fact that should we find some interesting data points or biomarkers that inform us about the aging process. I want to ask your opinion on your current thoughts on whether or not we can reverse aging or how you see us slowing down the aging process. Is it possible?
So I've had a lot of different plans over the years. At first, it was all about germline biology, which I still think is the root of aging and why we're even mortal in the first place. I still think curing menopause and andropause and going down that road is the best pathway at this point. But uh, replacement is there's making headway there on different replacement strategies. So that's really cool. I could see that happening, I mean, relatively quickly once certain core components are figured out. My own plan at this point is it's kind of like a 4-step process. Number one, can we just see what's going on accurately? And that's why I built this whole system. And then 2 is, okay, I'm going to get from one side of this curve to another side of this curve where people already exist. And that's natural variance. Both of these steps have kind of already been done to a certain extent. And so they're pretty conservative, and I think that they can be done relatively easily. We can get through those. The third step is, can we break out of the curve, which is, again, what Bryan Johnson did with that one biomarker, red cell distribution width. And then finally, can we turn those curves into flat lines? I have no idea how long it's going to take, but I do know that the process for doing that, like each of those steps feeds into each other. And so I think that we can actually go through every single one of these things and find out how to take this system that changes over time and figure out how to like flatline them on an individual basis. I don't know if it's possible to do that with everything, but the core concept seems sound at this point. And I've been talking to a lot of people, and I don't think anyone has tried it to do this correctly in the past. So that's my plan. I think that there's definitely like we see examples of non-aging organisms and non-aging cells all the time in the wild. So nature has already figured out how to do this. It's actually pretty trivial for things to just sort of exist forever. Uh, we're the weird things, like what we like multicellular somatic organisms that get created and die with the express purpose of just getting sort of like used up and destroyed and then discarded. That's the weird thing in nature. Like the majority of what nature is single-celled organisms that are capable of maintaining what's the phrase again? Physical continuity indefinitely. And it's really aggravating because that's like the game of life that's getting played at a sort of like a fundamental level, is that most of the life on this planet, by mass and by weight, or by mass and by population, most of the life on this planet is capable of being immortal. We aren't, because we're like these vehicles that these single-celled organisms have built around themselves and gone like to enormous complexity over time, over millions and millions of years. But we're the weird things, and the normal game of life is trying to stay alive forever. Like that's what life is actually doing, and it would be really nice if we could participate in that as well, rather than just sort of being vehicles that they use in their game. So nature has figured this out, and it'd be really great if we could copy nature. We've done so in the past. We've done it pretty well. We can build machines that go underwater longer than any living organism can, any mammal anyway. We've built flying machines that can go higher than any creature that exists that can fly. I think that it's very possible for us to figure out the nature of how these cells are living indefinitely, and then figure out how to build technology to allow us to get at least to some extent, massively extended lifespans.
A lot of these points that you've just mentioned, you summarized very nicely in this sort of paper that you put together. I can share with my audience the theory of biological mortality. I'll share it. And I liked one of the sentences, which was, "We are not the actual organism, the germline is." And would you be able to elaborate on your knowledge around like reproductive biology and what you really mean by this concept?
Yeah, so like when we walk around and we think, what is life? We are interacting with other, multicellular organisms, and that's for us, like we think like we look at a beaver or something, or like a giraffe, and we think, oh, that's the organism, like this giant thing, that's what the organism is. But actually it's like the world's full of these like mecha walkers or whatever, and there are these little pilots inside, which is the germline cells, and we are the walkers, right? We're these giant robots that they build around themselves, and then they just leave it, and then they build a new version, and they just keep doing this over and over again. And so there's some philosophy in there about the nature of cell division and physical continuity and identity that I won't get into, but suffice to say that there's some people that believe that like if a germ cell divides, then it essentially dies. I don't have that view. As long as it maintains physical continuity, then it's still alive. And if you take this view on life, then you look around and it's like the germline cells are the actual life forms here. Like that's the actual organism. And so really the division is like the egg and everything that's not the egg. That's the division between germline versus soma. That came out of trying to reconcile, because I was looking I had this theory of a while ago of like, oh yeah, there's germline cells and then there's like the soma around it. But I was thinking like male germline and female germline because I mean, classical biology is like, okay, there's a male germline, there's a female germline, and then there's the male soma and the female soma. But if you look at the rate of aging for the egg versus the female soma, it's different. It's a different relationship than the male germline and the male soma. And actually, Aubrey mentioned this to me during this conference in Dublin, and I was like, yeah, like that is true. And I was trying to reconcile that, and I was trying to think about like like how, why are the rates of aging different for the male germline, the female germline? And then one day I was just like, what if the male germline isn't actually, you know, the germline? What if it's just there's the egg and then everything that's not the egg? And now the female soma, the male soma, the male germline all fall in the same category. They're all over here, and then the egg is over here. And then if you look at every single organism through that lens, suddenly all these things start to make sense. Like why, like the construction of all these different organisms and why they're built the way that they are. It just makes a lot more sense from from an engineering perspective. Like a colony of ants is just, it's like if your arm could walk down the street and grab food and come back. That's what an ant colony is. The everything that's not the egg inside of that queen is just part of this body, and the fact that it can communicate across space through pheromone interactions is just a feature of this extended body. So like an ant colony, they call it like a superorganism. No, it's just an organism that has physical space between the components. So like if your cells could all dissociate and move around and then come back and reform, that's what an ant colony is. And so the structure, like the way that all this evolutionary pathways, just everything just makes a lot more sense when you look at it through that lens. So that's why I believe that now. I think that the germline is actually like that's the life form. And so if we can figure out how it maintains itself indefinitely, um, I think that's where we're going to find our answers. In terms of multicellular organisms, planarians are very interesting. The hydras, I don't know, not so much. It seems like we kind of figure out how hydras work, but with planarians, it's like a germline colony, and I don't know of many other organisms that operate like that, where it's like rather than your like in a human, the germline's on one location, whereas in a planarian, the germline is kind of like spread throughout the body. That's why you can chop it up and every single piece regrows a whole new planarian, because it's kind of like a bunch of germlines sort of hanging out in this sort of a collective mechanism situation. And that's very different from an evolutionary perspective than like most life on this planet. So I think that studying planarians is going to be really useful. And I wish I could do all of this stuff, but time is of the essence. So I think we've gone on about that for a while. There was something else that could have been covered. That tech tree stuff. It's not as relevant at this point. So when a few years ago, I built this massive overview of the whole longevity field, and then that led into a project for the Foresight Institute for building this sort of tech tree structure for trying to figure out the organization of all these different pathways and how far we're getting on any one particular pathway towards figuring out how to solve aging. And it was very good personally because I could see what all the bottlenecks were. As far as a descriptive tool, I think it's just very complex, and so it was hard to interact with, and a lot of people just couldn't, didn't figure out how to interact with it, and that's fine. But one of the things that came out of that was that across the board, I looked at every single one of these fields, and I saw that diagnostics were terrible. Like it wasn't just a few; it was like across the entire longevity field, diagnostics were just bad for everything. And that's one of the reasons why I built this AgeRank system, was because it's like, hey, we don't even know what normal aging even looks like for most of these things. How are we going to try to intervene if we can't even compare it to anything, right? So I thought it was incredibly useful for myself. I think it was hard for people to interact with, and ultimately, it's kind of been like waylaid. Um, so yeah, we'll see. I mean, it's just really complicated stuff, so it's difficult.
For sure. Yeah, I mean, if anything, it's been great to see that you have still used it though to build this AgeRank system, which I think is going to have even more value to the field. So, and that there definitely was a purpose, and there's been a successful outcome from it. But what else? I mean, you mentioned that you're working on many things at the moment. Is AgeRank your full-time sort of focus at the moment, or what other things are you looking at?
Um, let's see. I would say that AgeRank is like most of, in terms of the longevity stuff that I'm doing, that's most of it. Is there anything else? I'm helping Foresight again. They still want to try to get this tech tree thing to work, so I'm just helping out with that. And I'm open to other stuff, but I think my time is getting more scarce now. There's a lot of there's a lot of really cool next features for this diagnostic system. So uh, as far as AgeRank is concerned, there should be the ability to like have different graphs like overlaid on top of each other. I need to get more databases involved. I need to get like meta tags on these biomarkers. So if you want to say like, oh, I want to see everything involved with the kidney that changes with age, you should be able to just pull it up instantly. And then you're like, oh, well, I want to see everything that's within only like the last 5 years or something like of that. And then you can just be able to filter these biomarkers down and find these subsets and be like, okay, I want to see every biomarker that's been tested against this particular drug. You should be able to do that. And it should be just instant, right? So there's a lot of features. I think that are the next steps for that. And it just kind of depends on resources and how much support I can get for building this thing out.
Yeah, well, I think for sure, there should be. I mean, I'd love to see it develop. And so, just I guess more of a wrapping up sort of question. I've read some of your pieces of writing before. I've obviously spoken with you today, and love to hear your insights. And I'm just curious to know, why did you accumulate all this knowledge? Like, how did you go about learning so much about these different topics? Was it from reading textbooks, or how did you build up this intensive knowledge and insight into longevity?
Sure. Okay. So the first thing I did was just read like thousands of papers. And that's not an offhanded comment. It was actually like it was over thousands. At some point I just realized, it's not illegal to just start reading tons of things from Science Director, these other publishing sites. So you just start reading all these things and going down into these rabbit holes, and try to like have some sort of mental organization. But then the next layer of that is actually going out and talking to these people directly, because there's tons of things that they'll never put into these papers about like, oh, when we were doing that, here's what actually happened, and then we had to write it this way, but like actually so you get that level of insight. And then you have to go around and talk to all the people that are sort of into this so-called industry, which is, I don't think it's an industry yet, or it shouldn't be, but you talk to all these people and you find out like why they're doing it and what information they have, and I guess build up connections to people, find out like it's at this stage of it, there's so many people that are doing it for money rather than to try to actually solve the problem, that a lot of it is about filtering. It's about like, okay, is this person just trying to push their agenda, or are they actually trying to get something going here? And so that's been the most important thing for me. at this stage is like, how do you trying to figure out who seems like they're really doing something real versus just trying to make a buck.
Yeah, I agree. And so, I mean, where do you think then there should be more focus? Obviously, I'd agree that reproductive biology, understanding the oocyte aging is definitely something that we need to research more. But are there any other topics that you would like to see more work into?
Let's see. Hibernation is very interesting. So again, I don't mind saying this. I'll say this as many times as I need to. Reproductive aging is obviously number one, but apart from that, I like what Fauna Bio is doing. Their whole angle on it. As far as being a company, I'm not sure how legitimate they are, but they seem pretty real to me. The concept of going after hibernation mechanisms in mammals, understanding them, deconstructing them, and trying to rebuild them in humans is seems like a really good idea. And it's also one of those ideas that doesn't overlap a lot with other people's concepts. So they're kind of in a very unique position, and I like what they're doing. Um, the organ construction, organ printing and organ replacement, that's always like really important. I think external organs is a field that is like people don't think about it, but once we can build an organ, there's nothing from stopping you from like making a second pancreas or a second thymus and then just attaching it to yourself. Like like some kind of like a hybrid, like once we get stable septa to work and that kind of stuff, we can just like add organs and then we can design organs that have never existed. So that whole organ construction field um, can sort of blow up in ways that people aren't really even imagining at this point in time. So that's another piece, and I think those are like the other two like leading fields that I think are undervalued at this point.
Yeah, for sure. So, well, Aaron, it's been great talking to you. I mean, it's just amazing your insights. I love the way that you describe things, and your writing's been epic. And it's just, I can only wish you the best of luck with building AgeRank further, and hopefully you see many people use it. And yeah, it's been great having this chance to talk to you, and I appreciate you taking the time out of your busy schedule to do this. So, yeah, thank you.
Yeah, no problem. Thanks for having me. I like your videos and what you're doing, and I hope that when you finish your PhD, then you are able to really make a huge impact on the field in terms of like, even more than you already are. So
I hope so. I
best
mean,
of
I
luck
think
to you as well.
Thank you. And I agree with your point. I think, yeah, just talking to people and hearing from them in person their thoughts is almost as valuable as reading like papers, which I know are somewhat skewed or like they fit the narrative that people want to
Yeah.
see. So I'm 100% in agreement with that. So yeah, no, thank you for coming on. It's just been great fun.
All right. Take care, and I'll see you in the future.